Welcome back to Derivatives and Risk Education. In this video, we explore a central concept in financial mathematics, martingales. Martingales are stochastic processes that model fair games, and in finance, they're the backbone of risk-neutral pricing. But why do we care about martingales? Because they give us a clean mathematical way to express fair value. If a discounted price process is a martingale, it means that, given everything we know today, the expected future value is exactly today's value. No drift, no bias, no arbitrage, just a fair game. And this is the key behind risk-neutral valuation. If we discount future payoffs at the risk-free rate and use risk-neutral probabilities, then the expected value of any asset is its current price. And here's the crucial point. We choose the risk-neutral probabilities precisely to make the discounted price process a martingale. That's what defines them. Not historical data or investor beliefs, but the requirement that discounted prices behave like fair games. Let's now define a martingale formally. A sequence of random variables, m0, m1, to big N is a martingale if m little n, so the random variable after little n tosses, is equal to the expected value, also after n tosses, of the random variable after n plus 1 tosses. And this needs to be true for all values of little n from 0 all the way to big N minus 1. Here, each random variable m little n depends only on the first little n coin tosses. We call this an adapted process. We can also define two related concepts. Sub-martingale satisfies m little n is less than or equal to the expected value of the random variable after n plus 1 tosses. This means the process tends to increase in expectation, or at least not decrease. And a super-martingale satisfies m of n is greater than or equal to the expected value at n plus 1. So this process tends to decrease in expectation, or at least not increase. These definitions generalize the martingale condition to allow for directional drift. Now let's look at an example of verifying the martingale condition using risk-neutral probabilities. Suppose that the interest rate R is 10%, so 0.1. The stock price at time 2 is 100, and at time 3 the stock can go up if the coin toss is heads to 120, or down if it is tails to 90. Now, we've already seen how to compute the risk-neutral probability in a previous video using this formula for P. Here, U equals 120 divided by 100, so 1.2, and similarly D equals 0.9. So we can plug in the values for U, D, and R into the formula for P, which gives 2/3. Now let's check if the discounted stock price is a martingale under this P of 2/3. As a first step, we compute the discounted values. For that, we will need the values of 1 plus R to the power of 2 and 3 shown here. So the stock price at time 2 of 100, discounted back to today, is 82.64. And similarly, the discounted prices at time 3 in the heads and tails scenario for the third coin toss are 90.16 and 67.62, respectively. Then, as the second step, we compute the expected discounted value at time 2 of the stock price at time 3. This expected value is equal to the probability P of heads of 2/3 times the stock price in the head scenario of 90.16 plus the probability of tails, so 1/3, times the price for tails, which was 67.62. Altogether, this equals 82.64. And this matches the discounted value at time 2, which we saw earlier. So the discounted stock price is indeed a martingale under the risk-neutral probability P equals 2/3. Martingales have two powerful properties that make them ideal for pricing. First of all, time consistency. This means the expected future value, conditioned on today, is always today's value. And constant expectation. Unconditional expectation stays fixed over time. These properties ensure that fair value is preserved across time and across paths. Martingales link directly to the condition of no arbitrage and to risk-neutral pricing. To be precise, if the discounted wealth process is a martingale under a risk-neutral measure, then no arbitrage is possible. This leads directly to the risk-neutral pricing formula. Let V big N be the payoff of a derivative at time big N, then its price at time little n is equal to the expected value at time little n of the payoff V at time big N, discounted from big N to little n. This formula works because the discounted value process is a martingale under the risk-neutral measure by construction. So to recap, martingales express the idea of fair value, no drift and no arbitrage. We choose risk-neutral probabilities so that discounted prices become martingales. This leads to consistent pricing formulas and replicable hedging strategies. The risk-neutral pricing formula applies to single payoffs and to full cash flow streams. Thanks for watching. Don't forget to like, subscribe, and share with anyone learning quant finance.